In this session, we are going to discuss classification of integral equation. We are going to, first one is linear and nonlinear integral equation. Second one is integral equation of the first and second kind. Third, the homogeneous and non-homogeneous integral equation. Fourth, Fredholm's and Volterra's integral equation. And the last one is other forms of classification. We start by taking linear and nonlinear integral equation. To classify integral equation, based either it's linear or non-linear. First, you have to check the linearity of the unknown function y of s. Let's consider the following equation. In the first equation, you can easily see that this is our unknown function, and it also appears under the integral sign on the other side. And checking the linearity of the unknown function, you can see that this is using the power of 1, this is also using the power of 1. So the first equation is what? Linear. Moving on to the second equation, this is our unknown function, and it also appears under the integral sign here. So you can easily see that the power of the unknown function on the other side is using the power 2, and the other on the one under the integral sign is also using the power of 1. Since this one is using the power 2, it makes the integral equation to be non-linear. The last one here, looking for the unknown function. The unknown function appears only under the integral sign, and it's having the power of 1, all right, but it's found in a transcendental function, which is sine. So it makes it find the transcendental function. It makes it to be non-linear. So whenever the unknown function appears in a transcendental function, it makes the IE to be non-linear. Move on by taking the second one, integral equation of the first and second kind. Let's consider the following equations. In our first equation, you can easily see that the unknown function appears only under the integral sign, does not appear anywhere again. So since it only appears under the integral sign, it makes this equation is known as first kind integral equation. And to the second equation, you can see that the unknown function appears on one side of the equation and also appears under the integral sign. So this integral equation is of the second kind. Now let's move on to the third one, homogeneous and non-homogeneous integral equation. So homogeneous and non-homogeneous integral equation. Whenever the free term f of s is equal to 0 in the integral equation, this makes the integral equation to be homogeneous. And it always has a trivial solution. Y of s is equal to 0. Otherwise, it's it is a non-homogeneous integral equation. That is when f of s is not equal to 0. That's the free term is not equal to 0. So let's consider the equation. This is a general form of an integral equation. General form of integral equation. So if this is equal to 0, we are going to get y of s to be equal to lambda integral of a to b a of st y of t dt. Since f of s is equal to 0, it makes this equation to be a homogeneous integral equation. Now, and we are saying that it's homogeneous and it always has a trivial solution, y of s is equal to 0. Now, if the value saying that the value of lambda of the homogeneous equation with non-trivial solution, that is y of s is not equal to 0, is called eigenvalue. of the kernel of the corresponding homogeneous equation. The solution y of s is the eigenfunction. Is the eigenfunction. So this is all about homogeneous and non-homogeneous integral equations. We are moving on to symmetric kernels. Let's tackle symmetric kernels under the homogeneous and non-homogeneous equation. Symmetric kernels. A kernel is said to be symmetric if k of st is equal to k of ts. That means if you're touching the s and the t's, you should get the same function. So that's the meaning of symmetric kernels. Properties of symmetric kernels. One, for all symmetric kernels, there exists at least one eigenvalue. For all second one is that all the eigenvalues of symmetric kernels are real. In the third one, we're going to say that eigenfunction phi of s and phi of s and psi of s of symmetric kernels corresponding to distinct eigenvalues lambda 1 and lambda 2. That is, lambda 1 is not equal to lambda 2 is orthogonal in the fundamental interval a, b. That is integral from a to b, phi of s and psi of s is equal to 0. That means it phi of s and psi of s will be what? Orthogonal functions. Now we are moving on to Fredholm's and Volterra's integral equations. Let's take Fredholm's integral equations. Let's consider the following equations. So, in these equations, if a and b are constant in the equation, that is the limits of integration are constant, therefore the equation becomes a Fredholm's integral equation. Alright, let's name our first equation. We know that the unknown function appears only under the integral sign, so it's a first kind integral equation. So we're going to name this integral equation as a Fredholm's Fredholm's integral equation, the second kind, or the first kind, And this, in the second equation, you can easily say the unknown function y of s is here, and also appears another integral sign, and a and b are constant. So this becomes Fredholm's integral equation of the second kind. We move on by tackling Volterra's integral equation. In the Volterra's integral equation, if the constant b in these two equations changes to variable s, therefore this equation is being transformed into Volterra's integral equations. So that is so we change the b here, it's now not a constant anymore. We change it to s, which is a variable. So this makes the first equation to be Volterra's integral equation. But you can easily classify this, since it's a first kind integral equation, you can classify it as Volterra's integral equation of the first kind. And coming to this side, we change the b here to a variable s. And so this becomes since here it appears the unknown function is here, and also it's also here. It's a second kind integral equation. Then we can classify this equation as Volterra's integral equation of the second kind. Note: The note is saying that if the kernel K of st and the free term or the forcing term f of s are continuously differentiable functions, and K of st is not equal to 0 for a less than or equal to s, which is less than or equal to b, then the Volterra's integral equation of the first kind can be converted to Volterra's integral equation of the second kind. We will tackle this in our next session. So let's continue by looking at other forms of classifications. So we are just going to pick a specific form there, which is known as Integro-differential. Integro-differential equations. As the name says, integral differential equation. That's integro-differential equations. It is the definition says that integral differential equation is an equation in which the unknown function occurs as ordinary derivative on one side and appears on the other side under an integral sign. Examples. This is our first example. You can easily see that this is our unknown function, this is also our unknown function. But this unknown function appears on the left hand side as what? The derivative of what? Y. And appears on the other side under the integral sign. So this makes this equation to be integral differential equation. Let's try to name this equation. You can easily see that our limits are from 0 to what? S. A constant to what? A variable S. So this is a Volterra. So we are going to name this equation as Volterra's integral differential equation. Our last example is This is our last example, and we easily see that the known function appears here as ordinary derivative, and this side another integral sign. So if we check the limits of integrations from 0 to 1, 0 to 1 is a constant. So this makes this equation to be a Fredholm's integro-differential equations. So this is all we can do about classification of integral equation. In our next session, we will take a question to investigate either a function is a solution to integral equation, and also try to convert Volterra's integral equation of the first kind to the second kind. Thank you.